And here we have some examples of image of this kind of galaxies. And you can see as these objects appear in the sky as a very faint galaxies respective background. And this talk us about of this difficult to observe this kind of galaxies in general. A few years ago, in this work from by Van Dokkum and collaborators, with observations done in the coma clusters, they report the 47 LSBs objects, and they propose formally the term ultra-diffuse galaxies or UDGs, including two conditions. One, in the surface brightness, similar to the work by Sandage and Jelly, and also include a cutoff in the effective radius. So in general, the definition of UDGs correspond to a galaxy with an effective radius about of 1.5 kiloparsec or highest, and surface brightness of 24 magnitudes per second squared or more. And again, you can see some of these images for these galaxies, but in this case, taken with this with this array of lengths, call it a dragonfly or DF, and consequently the name of the objects DF1, DF2, DF3, and others. This sample of galaxies or UDGs include some polemical galaxies, as for example the case of the DF2 and your deficit of dark matter. But taking into account that this estimation was realized with few globular clusters. And in other articles, in other works, for example, in this by Amorisco, they talk about the problem of estimation of the mass in relation to the number of globular clusters that you observe. And in the same way, in this other work by Jess Doppel and Laura Sales and other collaborators, they again show the large scatter in this estimation problem in relation to the mass, in relation to the number of globular clusters that we observe. And for the case that you consider few globular clusters, the measures of the mass could be over or subestimate, that you can see in the left plot. In general, we consider in the scaling relations, in this case, correspond to a relation between sizes for the galaxies and the magnitudes or luminosities. When you can see different kind of galaxies. Here on the left, we have the normal population of galaxies, where this relation is well defined. Just for have some numbers in mind, the Milky Way corresponds to a galaxy with this value of stellar mass and scale radius in the disk. But on the right, in the range of the dwarf galaxies, this relation show a large scatter in the size at a fixed magnitude or stellar mass. So we have both extended and compact galaxies at the same magnitude. And in this presentation, obviously, we will focus on those extended populations that includes principally the sample of UDGs, but maybe could be include the population of LSBs. Typically, traditionally, like I show in previous slides, by the work of Van Dokkum, Sandage, and others, traditionally, these UDGs live in clusters But in other words, we have the reports of this kind of galaxies into the field. So it's important to study these populations of UDGs and LSBs in all environments and their respective properties, like, for example, the stellar populations, the metallicity, the morphologies, and other kind of properties. So,
Sorry to bother you. Your mic is making a slight noise. I think it's just like touching something with your in your face or your shirt. You can adjust
uh,
it so it doesn't touch anything.
okay, I try to speak more near for my microphone.
That's fine. That's
Okay,
that's
okay, it's fine.
sorry.
Continue from here or previous slides.
Oh, that's fine.
Okay, okay.
That's okay.
So our motivation is to study this kind of galaxies with similar sizes to major galaxies like the Milky Way, but with several differences in their masses, with 2 or 3 orders of magnitude of difference. Again, in previous talk, Galas talked about of these giant sizes is very confused because really this comparison between UDGs and large galaxies, like for example the Milky Way, correspond only 1% of this population of UDGs, because the rest of this have sizes more similar to the population of dwarf galaxies. But it's interesting and try the capture the attention of the people. So in this way, one question is how are UDGs formed into the lambda cold dark matter scenario? And for this, we use data from the TNG Illustris project, and in particular, we use data from the TNG Illustris 50 simulation. And there, we looking for these UDGs in all environments and study their respective properties. One comment about this special simulation, TNG50, is a simulation that has a great resolution per particles, invariance, and dark matter. So we can resolve and analyze the populations of dwarf galaxies with good details. Again, just to have some numbers in mind, for example, one galaxy of more or less 10 to 8 solar masses, it has around of 2000 stellar particles. This talk us about their great resolution in this simulation. Now I continue with this first part when I present some review about of the formation mechanisms for the formation of the UDGs in general. But previous of this, we define our UDGs, those galaxies with stellar masses in the range of the dwarf population between 10 to the 7.5 to 10 to 9 solar masses, above of the 95% on the mass size distribution, or similar, our population of UDGs correspond to the highest 5% in the distribution mass stellar mass, size stellar masses. And these are highlighted in this plot with blue and red circles. And only for comparisons, we include some observational data with grid symbols. And we can see how our definition overlaps very well with the observational data, and also with this definition from Van Dokkum with cutoff into the surface brightness and the effective radius. This sample of UDGs is divided into populations. 260 satellites located into the high density regions, like groups or clusters, and others, 166 centrals located into the low density environments or into the field. Um, Between other properties in this plot, I present the relation between color and stellar masses for all galaxies in the simulation, but in the range of the dwarf galaxies, represent here with gray dots, and again include some of observational data. And maybe could be strange these mixture populations of blue stars located into the red sequence and red circles located into the blue cloud. So in the case of the central UDGs located into the red sequence, this correspond to a special population of UDGs originated from backsplash orbits that I try to explain in the second part. And on the other hand, this population of satellites located into the blue cloud correspond to a sample of resonant fallers that preserve their properties of galaxies into the field. Other interesting point is highlight the relation between the abundance of UDGs in relation to the halo mass of the host. That following a known power law relation, and again we present the abundance of our sample of UDGs in the TNG50 simulation, and you can see how present a good agreement with the observational data. So talk about of the mechanisms of formation of UDGs. In general, in the literature, we can find different mechanisms of formation, and here I highlight some of these. For example, consider the UDGs as a failed Milky Ways. Consider the UDGs that their extended sizes is a direct consequence of the feedback. Also consider that these kind of galaxies born from the remnants of the interactions, for example, the mergers or tidal remnants. Consider that this population, the sizes of this population is related to the tidal heating effects, or like you can see in previous talks by Galaz and Perez Montaño, related to the excess of angular momentum in the dark matter halos. So in particular, we will focus in these three mechanisms of formation. RUDGs correspond to a failed Milky Ways. These mechanisms consider the population of UDGs as a normal galaxies in large gas and dark matter content that lost their gas along the interaction inside the cluster, for example, leaving an extent an incomplete galaxy that could not form the rest of the star content. For try to see this in these plots, in both plots, we take again the gray dots correspond to the all galaxies in the simulation in the range of the dwarf galaxies, and we include the abundance matching relations by Guo, Verossi, Almosters, and collaborators. And the main idea in this plot is show that this population of UDGs are allocated in this halo mass relation very well respect to the rest of the dwarf galaxies. This talk us about of this population of UDGs are not failed Milky Ways. Correspond to some kind of special galaxies inside the normal dark matter halos for their correspond stellar mass. Are the UDGs a consequence of the tidal heating? This is a very interesting mechanism of formation, but by definition have a problem, and is that only apply or principally apply to satellites because for the case of the centrals, it's very difficult only through the major mergers consider this kind of interaction and try to remove an important dark matter content. But the idea is that a galaxy inside the high density environments, groups or clusters, experiment several tidal forces that remove an important content of the material of the galaxy, baryons and dark matter, and also extended their size of the galaxy. Uh, Here on the left, we have a plot with we present the fraction, but in stellar and dark matter content at redshift 0, respect to the maximum value along the time. And you can see how this population of satellites mainly they lost an important content both on stars and dark matter. Again, just to have some numbers in mind, values of minus zero point 0.1 correspond to galaxies that conserve about the 80% of the maximum value along the time, and values of minus zero point 0.0 to galaxies that conserve only about the 30% of the maximum values. And you can see how this population of satellites lost an important content of stellar particles, but lost so much dark matter content of the dark matter halos. All of this in good agreement with this model by Carlette. In other similar work, Laura Sales and collaborators also consider as a possible scenario of formation of UDGs following these tidal heating mechanisms. In this work, they consider two populations of UDGs or LSBs. One of these that born into the field or BUDGs, and other population that the large sizes is a direct consequence of the tidal effect of the cluster, call it TUDGs. So for this, we measure the sizes values for our sample of UDGs before the infall in relation to the values of sizes at redshift 0. And we observe that the major part of our satellites preserve their sizes along the interaction. And only around of 30% increase their size by 25%, and less of the 10% of our population reach a growth around or above of 50% their initial values. So even in these extreme cases where the galaxies increase their sizes above of the 50%, we can observe interesting examples in two different ways. One population experiment an extreme rapid expansion, and other population experiment a secular expansion. But also is interesting to observe how after the first pericenter passage, the galaxy lost their gas content and cut off their star formation. Um, in this way, we can consider the tidal heating as a possible mechanism of formation of UDGs, but not an efficient mechanism because only apply to a small part of the sample of the galaxies, and also only apply for galaxies into the groups or clusters. So finally, for this part, another interesting mechanism of formation is this proposed by Amorisco and Loeb, where they consider the UDGs as galaxies that were born in halos with high spin values. The idea is that the large sizes of the UDGs and LSBs are a direct consequence of the excess of angular momentum of the dark matter halos, following these known halo mass scaling relations. Um, in this plot, we can see the distribution of spin parameters for the halo. Again, the gray dots correspond to the population of of the normal dwarf galaxies, and the black and green lines represent the distribution of the spin values per beam of stellar mass for centrals and satellites. And you can see how, in both cases, are in good agreement with this theoretical known value about of 0.035. All of this in contrast with this distribution for the spin parameters for the UDGs, again, in blue and for centrals and red for the satellites. In both cases, present a high values respect to the population of the normal dwarf galaxies. Again, this is in good agreement with this idea that the extended galaxies is a consequence of the excess of angular momentum. And again, this is an interesting, and we believe that is a good mechanism to the formation of the extended galaxies in general. Again, in good agreement, we can saw in previous great talks by Galás and Pérez Montaño that study this kind of population of LSBs. So a brief summary for this part of the talk. When you consider these three possible mechanisms of formation, then we discard this like a possible failed Milky Ways, but we consider that the possibility, the contribution of the tidal heating and the contribution of the angular momentum in the formation of the UDGs. But maybe, but this is not a finally model of the formation of UDGs, because it's continue like a open problem in the formation of this kind of galaxy, and maybe is correspond to a mixture for this and other mechanisms. So in this second part, let me talk about of this particular population of quiescent UDGs into the field. This is very strange because we have a very remarkable properties of the galaxies that dependent to their respective environments. We expect that the galaxies into the groups are preferentially gas poor with all star populations, preferentially correspond to red or quiescent galaxies with morphologies preferentially ellipticals or spheroidals, in contrast to the galaxies into the field that correspond to gas-rich galaxies with joint stellar population, appear like a blue or star-forming galaxies with some kind of structures, disky or spirals. And in general, these apply to the population of UDGs and LSBs in general. And again, into the field, effectively, this happened. Uh, but the people has found this kind of quiescent UDGs into the field. And one questions that you can do is what these galaxies doing into the field, or how did they quench? And again, for try to encourage this problem, we have the same previous sample of UDGs, but in this case, we only focus in the population of central UDGs. Again, in the plot of the color respect to the stellar masses, um, we found that in the low density environments, the UDG are typically blue. But to our surprise, we find this population of red UDGs located or that occupies the, the red sequence. And again, uh, we we refer to these populations like blue UDGs and red UDGs. And this color correlated very well with the star formation, where the blue population correspond to a star forming galaxies located into the main sequence. So these two populations, red and blue UDGs into the field, separate in other properties as well, as for example, in the right panel, we have the differences in the ages of star populations, where the star forming are very young, in contrast with the old population for the quiescent UDGs. And again, for the observational reference, we include this yellow diamond that correspond to the average of a sample of UDGs in the coma cluster. And the blue diamond correspond to the average of the observational data from the UDGs start forming into the field. In the center panel, on the center panel, we have the kappa rod parameter that is a great estimator for the morphologies of the galaxies in general. And above of zero point 0.5, we have preferentially these structures, and below preferentially spherical morphology. So our population of red UDGs are all spherical dominated, and some part of our blue UDGs have some kind of the disk structures. And on the other hand, in the right panel, we have the halo mass relation, and you can see that those quenched galaxies are dark matter deficient compared to the blue population, and that follow very well this abundance matching relation. And again, the question is where they stripped. When we reviewed the information of this sample of UDGs, we observed that all of this has a passage through the massive halo with virial masses in range of the 10 to the uh, uh, um, 12.5 to 10 to 14. And these UDGs, is important to comment that all of these UDGs bore into the field as UDGs. After of this, fell into the massive halos. There, they lost their gas content and came back to the field as quenched galaxies. This is in short words, the mechanisms to formation of these quiescent UDGs. So in contrast with the we expect and unexpect for galaxies into the field, but like I comment, these both populations are being observed into the field. Here we have again some kind of gallery of our sample of UDGs formed through this schematic process presented on the right panel. Our sample of UDGs are located about of 2 times the virial radius of the nearest group. Only for take some numbers in mind, if in the case, for example, the Milky Way with a virial radius about of 150 kiloparsec, we expect to observe one of these quiescent UDGs about of 300 kiloparsec, or in the case of coma with about of 2 megaparsec of virial radius, we expect to observe these galaxies about 4 megaparsec. This is correspond to a very low density environments or very isolated. And this overlaps very well with other sample of isolated UDGs located in this distance. And we found one extreme case of these backsplash UDGs that this example is very particular and very setting and very interesting because was preprocessed into a group previously to the info into the major halo, and finally was ejected about to 3.5 megaparsec away. Correspond again a very extreme case, but remember that this distance can be scaled with the Villard radius of the system. Another interesting point is the kind of the orbits of our backsplash UDGs. And in this many cases, these orbits are very radial, and for the same reason have the more probability to have been backsplash galaxies. Uh, this plot and these other results where we send our thanks to Chris Mejor for this apport for the calculus of the beta values for this population of UDGs. In general, in this process, as a consequence of the interaction of these massive halos, our sample of UDGs lost their gas content. Consequently, stopped their star formation, and similar to the population of these central quasi-UDGs, these stop increase their sizes, very similar to the satellite population. This is very important because, again, our population of UDGs were UDGs before the interaction. Okay, this is important because don't experiment a great effects of the tidal heating mechanisms.
Jose, there's 10 minutes left.
Okay, and as we expect, these galaxies lost an important content of the dark matter halo. Again, so just for a brief summary of this part, our find this population of UDGs into the field that are mostly correspond to the star forming population, but about of the 25% of these correspond to a quiescent UDGs. All of these, again, are located about of 2 times the Villard radius of the Nereus halo, and similar to the population of satellites into the high density environments. This interaction in the past didn't change their sizes, or in other words, the tidal heating don't correspond to a great mechanisms to form this kind of UDGs. And thank you.
Very nice talk, Jose. Now we have time for some questions in the audience.
Let me see. I can see you.
Thank you. Very nice, very complete work. I would like to know if you measured the concentration of the halos. You measured the spin parameter. You find that the UDGs could be associated to large spin parameters. But what about the concentration, especially in those cases where tidal heating is in action or any process? They are lower concentration halos in these cases, or did you explore that?
Thanks for this good question, because I can talk about this, but we check not the concentration, but for example the profile of the dark matter halos, and we can see how in the inner regions for these populations of UDGs, both satellites and central correspond present the same profile in the inner regions. Okay, but I don't know if your question is about if we realize some contrast between the UDGs respect to the normal dwarf galaxies. In this way, no, we don't compare these two profiles between UDGs respect to the normal dwarf galaxies, but it's a good task.
It would be interesting to see if low concentrations promote more the expansion, let's say, by tidal heating or by feedback or by the star bursting processes. Yeah, this can expand the galaxies by heating mechanisms, especially when the halos are low concentrated. So it would be interesting to measure this concentration for your UDGs. Just a suggestion.
Gracias. We try to check this, and okay, thanks for the effort.
Have more questions here in the audience?
Hello, thank you for the talk. So I have a question and a comment. Do you comment about the profiles of these UDGs, the dark matter profiles, mainly towards the inner regions? And the comment is because, as you know, dwarf galaxies with low star formation rates and with the small baryonic feedback effects are known to be in tension with the lambda CDM, because they are expected to be cored towards the center instead of the Caspi profiles, which cannot be lowered due to the feedback, baryonic feedback. So could you comment on that?
I'm not sure if I understand your question, but the idea of the dark matter profiles in both populations, centrals or satellites, present again the very similar profile in the inner regions, because like I present in the outskirts, like a consequence of this stripping, the profiles is very different. I don't check the gas profile, because the gas in general is very difficult to because the form that is dispersed into the halo is more difficult. Try to
Okay, but the resolution you are working with allows you to infer the steepness of the inner part of the dark matter density profile or not, regarding the core cast problem?
I don't know, but I remember that we checked some of this because the gas content is very extended in all the galaxy, not in the inner regions in general. Is our feeling about this distribution of the gas.
Okay, Dr. Galaz, if you want to ask your question.
Yes, thank you very much. Thanks, Jose, for your talk. Very interesting. I am glad to see that the models are allowing, to obtain more insight on these galaxies. It's very nice to see that. One thing that I want just to precise, which is something that turning around in many conferences in this subject, is that Van Dokkum precise that he cataloged these galaxies, ultra-diffuse galaxies, many of them, almost half of the sample he has in coma, as galaxies of the size of the Milky Way. But there was a large polemic about that, because he uses the effective radius. The effective radius of our Milky Way is about 1.5 or something kiloparsec, 1 kiloparsec. But we all know that this is not the size of the Milky Way. 1 kiloparsecs is about even less, a little bit more than the bulge, right?
Yes.
So the same criteria cannot be used for, I mean, you cannot use that criteria to define that another galaxy is of the size of the Milky Way because the effective radius is 1 or 1.5 kiloparsecs. Malin 1, for example, the galaxy just commented before, has an effective radius of about 2 or 3 kiloparsecs. Okay, but the galaxy is 200 kiloparsecs. So that is, I mean, there's a large discussion about how to define the size of these galaxies, which in fact are defined because the diffuse part, which almost defines the galaxy itself, is very large in the space. I mean, it's a huge thing. You cannot define the size of these galaxies using the effective radius. So it would be very interesting to see other sizes in the simulation and see if, I mean, what kind of sizes are better defined for these galaxies in terms of defining the complete size. This is one comment. And the other comment I want to add is if you have some insight on the dust of these galaxies using the models, whatever the dust could appear.
Okay. Thanks for these great comments. I try to check this because I understand this worst problem about of the sizes of the galaxies, but I understand. And remember other work in the people talk about of cut off with this misconception of the sizes for the Milky Ways and the UDGs. Thank you for your comment.
Thanks to you and nice talk. Thank you.
Okay, we have one last question here in the audience.
Thank you very much for the talk. It was a really nice talk. So I was wondering about the correlation between the spin parameter and being ultra-diffuse galaxy or not. So if you look to the merger history, or the merger tree history of the dark matter halo, and you follow the spin parameter, you will actually see that it really it behaves very stochastically, right? So sometimes you see that the spin parameter is above of the median, sometimes it's below, and not all the times the spin parameter stays constant with the time, right? So if there is a tight correlation between being a ultra-diffuse galaxy and the spin parameter, then sometimes you will see that when the dark matter halo has a low value of the spin parameter, you will actually think that is a high density galaxy, right? Rather than ultra-diffuse galaxy. I don't know if you can comment on that.
Thanks. It's a good comment because I checked this problem of the stochastic of the scatter in the spin parameters along the time, and for this we take some average in some scale time, try to reduce this noise in general in the spin parameter. Okay, we try to apply this or calculate this value the better possible. Try to remove this noise in general.
Okay, thank you very much, Jose. We can thank Jose again.
Thank you.